Welcome to today's lesson. I'm Guido Randolph, and today we are going to learn how to derive the general solution of the wave equation. So, our wave equation in one spatial variable x is given as utt equals c squared uxx. When you decide to bring everything to the left hand side, then you get this particular formula here. So, the general solution to our wave equation is just ux of t equals f of x plus ct then plus g of x minus ct. So in this tutorial, we are going to learn how to prove this particular formula here. So we are going to go through a very straight and easy to comprehend formula. That's the method of transformation. So with the method of transformation, what we do is that we transform the system to two first order PDEs. So you realize that our wave equation is a second order PDE. So we transform it to two first order PDEs. So remember that our wave equation is given in this form, and you see in algebra, then we can use it as a difference of two squared. So a squared minus b squared, and you know it can be factorized as a plus b times a minus b. So that means that our utt here minus c squared uxx here can be equal to, you see, a plus b. So u of t plus cu of x then times u of t minus cu of x. So that's what we have here. So we factorize our wave equation into two first order PDEs. Then when we are done, we introduce a new function v. Know that in some books you can see w or any variable. So we introduce a new function v by the relation. So we introduce a new function v such that our ut plus cux equals v. That means our transport equation equals that v. Alright, so because our transport equation equals this v, it follows that this v solves the backward transport equation. So it means that vt minus c vx equals 0, and we can prove why this statement holds. So remember, v is equal to the whole of this. So when you come down, we just put v. So this is v. But instead of v, we put everything here. So we get ut plus cuxt minus this. And when you simplify, you're going to get utt plus cuxt minus cuts minus c squared uss equals 0. So remember that from the clearance rule in our calculus, this is equal to this. So that means this 2 is going to give us 0. And you are going to get utt minus c squared uss equals 0. And we know this is the wave equation which is equal to 0. So that means we get 0 equals 0. So that means that indeed our v solved the backward transport equation. So as a result of that, then we get these two first order PDEs, ux plus cut equals v and vs minus c vt equals 0. So we've been able to transform our PDE now into these two we've been able to transform our wave equation, which is second order PDE, into these two first order PDEs. So with these two first order PDEs here, the one which is quite simple to solve is the second one, right? So we solve the second one first for v. So we have vt minus c vx equals 0. That's the backward transport equation. So this becomes the general solution for our v. We can show that here. So we have vt minus c vx equals 0. So using the method of characteristics to solve this, we are going to get dx dt equal to the negative c that we have here, and this will give us dx will be equal to negative c dt. When we integrate both sides, then we get x will be equal to minus ct plus a certain arbitrary constant. Let's name it s naught. So when you make s naught the side, you get s naught to be equal to s plus ct. And remember, our general solution is just a certain vx of t equals a certain f of x naught. And now our s naught is x plus ct. So that's why we say that our vx of t is equal to f of x plus ct. Then I return our attention to the first equation. So this is the first equation. So solving the first equation, we have ut plus cux equals v. So remember, there is a transport equation with a non-zero right hand side or a non-homogeneous term. So um we can solve the homogeneous part for our complementary solution and solve the non-homogeneous part for a particular solution. Then when we are done, we add them together. So solving our homogeneous part, you are going to get ut plus cux equals 0. And recall this looks just like the transport equation. So that's the transport equation. So when we solve it, you are going to get u of xt equal to jx minus ct. So if you don't understand how we got this, you can use the same formula here. So that means that our homogeneous solution, our complementary solution, is u of xt equals j of x minus ct. Then remember that our non-homogeneous term here is v, and we've already found for v in our second equation. So that means that our particular solution is up of xt equals f of x plus ct. This happens to be the solution for our v because the v is the non-homogeneous part. Hope you recall. So the general solution then is just u of xt equals the complementary solution plus the particular solution here plus the complementary solution, and you get this. So you realize that this is the same as the formula that we want to prove initially. So that's how to prove the general solution of the wave equation. In our next video, we will learn about the Lambert's formula and how to use it to solve for the solution of a wave equation uniquely. Thank you very much.